Hello, in this video we're going to be continuing section 5.5, which is all about alternating series, and I'm going to start off by defining what does it mean for a series to converge absolutely and to converge conditionally. So an infinite series, the sum from 1 to infinity of an converges absolutely if the series, the sum from 1 to infinity of the absolute value of an converges. So if the absolute value version of your series converges, then we say that that series converges absolutely. And then on the other hand, if the original series, the one with negative terms, converges but not the absolute value one, then you get conditional convergence. So on the other hand, the series converges conditionally if the regular sum of an converges but the sum of the absolute value of the terms does not. Okay, and so this brings us to a theorem which we call the absolute convergence test, right? Because for us to test, let's first highlight, right, this is also another vocabulary word, absolute convergence, convergence test, right? So for us to check if a series converges absolutely, then really what we have to check first is if the absolute value converges, because if the absolute value converges, then we're guaranteed that the original series also converges, right? And that makes sense because in the original one, things can cancel out, where in the absolute value one, we're making everything positive now, so you have more of a chance to go to infinity here with all positive terms versus having some terms potentially cancel out with the negative signs without the absolute value. Okay, so let's do some examples. So in these examples, we want to determine whether the series converges absolutely, converges conditionally, or diverges. So the first example that we'll do is going to be the sum from 1 to infinity of -1 to the n plus 1 all over n, right? And since we want to check, does it converge absolutely, the first thing we should check is, does the absolute value of that sequence converge, right? Because that's what the absolute convergence theorem says, is that if the absolute value converges, then we're guaranteed to have that. So if we want to check absolute convergence, we might as well start with this because we'll automatically get this, right? But if we don't get this, then we could just check this, right? But if we do get that this converges, then we don't even have to bother with this. Okay. So when we think about the absolute value of the sequence, what happens, right? The terms start alternating. So this is actually equals to the harmonic series, right? So this is the harmonic series, which we said that, what did we say about the harmonic series, right? The surprising finding was that the sequence 1 over n converges to 0. However, that the series diverges, right? So even though this sequence goes, right, smaller and smaller and smaller, the sums, right, the partial sums don't get smaller and smaller and smaller. They actually go off to infinity. And this is supposed to be an explanation point. Looked like a question mark, right? So we know that this diverges, right, because it's a p series with p equal to 1. And so we know then that this series, the negative 1 to the n plus 1 over n, does not converge absolutely by the absolute convergence test. Okay, so now what? Right, now we ruled out this first option for this example. Now we gotta check, does it converge conditionally or does it diverge? So now we want to look at the original series, right? So now see if the sum from n equals 1 to infinity of negative 1 to the n plus 1 over n converges, right? And so we can use the alternating series test on this because we know that this is an alternating series, and right, when we remove the alternating part, the 1 over n part is decreasing, so we can use that, right? So now we say use the alternating series test. Right, so this is 1 over, yeah, we're starting at 1 over 1 plus 1 over 2. Well, we're writing up the sequence terms now, so I'm not going to put the sums right now. 1 over 3, 1 over 4, dot, 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 right, because we know it's decreasing. Now we need to check, does the limit as n approaches infinity of an, right, that's the limit as n approaches infinity of 1 over n, and we know that that equals 0, right? And that fits our absolute convergence, right? So that means that by the alternating series test, sorry, not the absolute convergence, I'm so sorry. Therefore, by the alternating series test, right, the original series, the alternating series, converges. So, therefore, right, it converges conditionally. Because when we get that the absolute value doesn't converge, but the original one does, then that means we have conditional convergence. And so let's do one more example of these, where we're trying to determine how does it converge? Does it converge absolutely or conditionally? So this is the same, technically the same example, but part B. So we do the sum from 1 to infinity of cosine of n all over n squared, right? So since we want to check, does this converge absolutely, the first thing we'll do is check if the absolute value of that series converges. So we do the absolute value of cosine over n squared. Right, and so how are we going to do this? Well, remember, right, cosine is always stuck between negative 1 and 1. Right, so what does the absolute value of cosine mean, right? That means that all of these negative ones are going to become positive ones. So the absolute value of cosine of n, we know, is always less than or equal to 1. Oops. Right, so that's going to help us if we're trying to figure out what this converges to, right? We can use the comparison test, right? Because now we know that cosine of n over n squared is always less than or equal to 1 over n squared, right? The absolute value doesn't matter down in the denominator because n squared is always positive. So then we can use the comparison test with 1 over n squared. Perf. And then since we know, right, what kind of series is 1 over n squared? Right, that is a p series with p equals 2. We know that that series converges. Right, because we said series with p greater than 1 converged. Right, so then, right, so now we know that, therefore, right, we compared it to our absolute value of cosine over n squared. So that means that that one has to converge, right? Right, so therefore, so the final remark then is that the original series, right, without the absolute value sign, converges absolutely. Right, and that's by the absolute convergence test, because that test told us that if the absolute value version converges, then the original one does as well. And that's where I'll stop 5.5. Thank you guys.